Okay, welcome to part 4 of our lecture video series for Wednesday, April 19th, where we discuss how we can quantify or calculate heat Q. So in order to talk about heat, we need to remind ourselves about the relationship between thermal energy and temperature. So recall, when we're talking about the temperature of the system, like a physical property that you and I could go into the lab and measure, temperature is telling us on average the amount of kinetic energy that our particles have in the system, which is thus something that is converted into thermal energy. So, like if I've got some state at some initial temperature, that's our way of describing kind of how much thermal energy is in the system. Not, exactly one to one, right? Because temperature is in some kind of like degree unit, and we know that thermal energy is in a joule unit. But in general, when we're talking about temperature, we're talking about thermal energy found inside the system. So then where does that leave heat? So let's define heat, Q. So heat is the amount of thermal energy transfer across some temperature gradient, temperature difference, which we'll call delta T. So for example, if I have a system that is at some initial temperature, and then I am at some new final temperature, then the heat that is exchanged or changed or evolved is going to be related to the change in temperature across these two things. So let's kind of break this down a little bit. We've got, sorry, I'm being so picky with color today. Heat, which we says is dependent or related to in some way to a change in temperature. So let's ask ourselves, in what manner are heat and some temperature difference related? Meaning, like, what kind of function would model how a change in heat would result in some kind of change in temperature, or vice versa? So let's imagine that we've got, I don't know, some temperature scale here that goes from 0 to some max temperature. If I were to look at a starting temperature of 0 to some final temperature here, Tf, then this delta T is equal to Tf, and I would have some Q that is related to that amount of temperature change. All right, what if then I had a change from Tf all the way to Tmax? So this temperature change, delta T, would be Tmax minus what we called the final temperature of our first temperature change, this guy. And we know that there is going to be some Q associated with that temperature change. Now, looking at these two differences in temperature, here in orange and here in blue, we see that the larger the difference in temperature, the larger the amount of heat or energy transfer is happening in our system as a result of that temperature change. So I could say the heat transfer Q that's happening in orange has got to be less than the heat transfer Q that's happening in blue, simply because the change in temperature happening here in orange is less than the change in temperature that's happening here in blue. How does this help us answer this question of how heat and temperature are related? So as we increase our change in temperature, Q increased, which means the opposite is true. As we decreased the magnitude of our temperature change, then Q decreased. And what is it mathematically that describes a trend in one resulting in the same trend of another? In other words, some change in our independent variable resulting in the same change in our dependent variable. So if something goes up, the other goes up, or something goes down, the other goes down. We call this a direct proportionality. Meaning that I could relate Q and temperature by some kind of direct proportionality. That's what this little alpha means. Q and delta T are directly related. Now let's remember another way of writing this. So what does this look like math-wise? So let's think back to things that we've seen that are directly and inversely proportional. So let's see here. So a direct proportion, let's see here. Why am I not able to think of something that we've seen that is a direct proportion? Okay, how about this one? As we increase the mass of a solid, we are also increasing the volume of that solid, right? A teaspoon of sugar or an ounce of sugar takes up less space than a pound of sugar, which will take up more space. So an increase resulting in an increase. What did we do that said they were related by some proportionality constant? So math function that we're looking at here means we're related by some proportionality constant. So what would that proportionality constant be in this example of mass and volume? So what relates mass and volume? Density would be the proportionality constant. And we know that density is a quotient of mass and volume. So mathematically, we saw that the quotient is equal to our constant. Another example of a direct proportion that I now finally remembered is Beer's law. So another direct proportion was that as you increase concentration C, you should also see the increase in the absorbance of a particular colored solution. So since we have the same trend in both variable, this means that they are related by a proportionality constant. And if you remember Beer's law, this said that this was epsilon for the molar absorptivity coefficient times path length times C. In other words, if I were to rearrange this and get just my proportionality constant by itself, I would have that absorbance over concentration is equal to that proportionality constant, which is the product of my molar absorptivity coefficient and my path length. And again, we see a division. So if we were to think about how Q and delta T might be related, we would say that Q over delta T is equal to some constant. And we have a name for this constant. Let's define something known as the heat capacity, C. So this is a physical property of a substance, so it's substance specific. And this is a measure of how much energy you would need to increase the temperature of a material by 1.0 degrees centigrade. So I could say that Q is equal to, well, let's keep going with our math. I could say that Q over delta T is then equal to our heat capacity, C. Or if I rearrange, I would get that Q is equal to C delta T. Now, this is definitely a way to quantify heat. So this is our heat quantification or heat equation. However, I don't want to bring too much focus on this because there's another thing that we're kind of not thinking about. So this is like, okay, I'm fine with this, but there's more to the story. So I'll leave you with a question at the end of this lecture. So, question. When changing the temperature of a substance, what else is going to affect that change in temperature? So it can't just be that heat is equal to delta T times a constant, right? Because even though this little heat capacity here is in fact specific to a substance, what we've yet to think about is not just what the substance is, but also something else. So I'll let you chew on this for a minute, and when we come back to see each other on Friday, when we come back to lecture on Friday, we're going to finish how we quantify heat, Q, by answering this question that I've left off with, and then we will begin talking about how heat is transferred between objects, and that will allow us to continue our conversation of thermochemistry. So have a good day tomorrow. Remember, we are not meeting, it's a flex day. So there's no instruction happening tomorrow, but I will be posting lectures on Friday, and I'll be seeing you next week on Tuesday. So thanks, guys.